Hello, my name is Paul Atilola. I'm your GTA for the semester. Okay, so I'll be showing you a walkthrough demo for Lab Experiment 5, which is basically this implementation of the switch debouncing circuit. All right, so for this lab, you'll be needing four components. You'll be needing an SPDT switch, which is a single pole double throw switch, which is just right here indicated by my pen. You'll be needing a 4-bit binary counter circuit, which is here. That's a 74161 circuit. You also be needing a 7400 quad 2 input NAND gate for implementing your SR latch. And you'll be needing two quantities of a 10 kilo ohm resistor indicated by the resistor right here. So for your resistor, for you to know which of the resistors to use, you can look at the color coding on your resistor. So for a 10K ohm, you'll be reading a brown, black, and orange according to the color coding scheme. That's a 10K ohm resistor. All right, so what I'll be demonstrating is to demonstrate the several steps required for this particular lab experiment. So in your step one, the first thing you need to do is to test or to understand how your push button works. So on your lab manual, you will see three terminals. We have the C label, the NO label, and the NC label. Your C, which is your first terminal to the left, as indicated by the yellow wire here, is your center. So your center here is one terminal, and it's either connected to 5 volts or to ground. For the sake of step one, this will be connected to 5 volts, as you can see, connected to this, and we have a red wire connecting it to the power rail. The power rail connects that to 5 volts. Then at the center terminal, which is indicated by this red wire, is your normally open, and at the extreme to the right, which is indicated by this green wire, is your normally closed. So without pushing the push button at the default state, you have your center latch on internally to your normally closed. So meaning that if this is connected to 5 volt as it is now, then the monitor or the output of your normally connect terminal will show that is in a high state. So how did I wire this? These two gray wires connect normally closed and normally open to my diodes. You need to pay attention to DIO 8 and DIO 9 on the screen. So without pushing the push button, you could see the default state, like I said earlier, that the center is latched on to your normally closed. And so you could see that the DIO port, which is DIO 8, showing the, to be able to implement this, before I press the push button, which is just right here, you could see the results on the screen as indicated by your reader. What you could see here, you could see that the reader here, which is the DIO 8 indicating the state of the normally closed, you could see that normally closed is at state 1, that is, it's high. Because why? Your center, which is connected to 5 volts, makes a direct connection to your normally closed, and your normally closed goes through the DIO to ground. So you have a direct flow from 5 volts to ground. And that's why you have your normally closed connected to DIO 8 in the high state. If I press down the push button, you could see that the state changes. And now normally open now goes to 1, the normally closed goes to 0. When I release the push button, you could see that the states toggle again. Normally closed comes to state 1, and normally open goes to state 0. And so that's what you're required for in step 1. Now we'll be moving over to step 2. In step 2, what you need to do is to implement an SR latch using your NAND gates components. So over here is the NAND gates package that I used to implement my SR latch. So how did I do the wiring? I took my input to supply my source to my S and R input from my DL0 and DL1 respectively. So these orange wires are connected from DL0 and DL1. Go through this. If you trace this, you can see my DL0, which is this, comes into the first NAND gate, which is the left side of my NAND package, the 7400 package. And then my R goes into the second input of the NAND gate, second NAND gate input on the right side of my 7400 package. To implement this, just to show us a figure of what I'm talking about, if you scroll up to figure 4 in your lab manual, you would see the particular schematic of what you're supposed to implement in the lab. So to test the functionality of the SR latch, use the truth table to verify the correctness of your implementation. And so to do that, I'll be showing us exactly how this is done using my digital reader as my input to supply to my S state and my R state, and then my digital reader to show it's my output, which is the Q and the Q bar. So how did I do this? So just to complete my connection that I made, so the yellow wires are used for cross coupling the input to the output. So what you have here in the schematic in figure 4, you could see that the output of the first NAND gate, where you have your X connected to, you could see that it's being fed into the input, the second input of the second NAND gate, where you feed in your R input into. You could see, to show the implementation again, my S input, which is supplied by my DIO0, goes into the first input, the first NAND gate, and then the output of this first NAND gate, which is Q, is being cross-coupled by taking the output and feeding it into the input of the second NAND gate, where I have my R input, which is my reset. Then likewise, the output of the second NAND gate, which is my Q bar, is actually fed as the second input into the first NAND gate, where my S input is fed into. So this is how we have the SR latch implemented with a NAND gate, with 2 NAND gates. So to show how this works, I'll be running a demonstration now. So pay attention to DIO0 and DIO1 as my input. So I connected my DIO0 is to feed the S input, and my DIO1 feeds the R input. Then my DIO14 on the output is reflecting the state of Q, and my DIO15 is reflecting the state of Q bar. So in this state, I have my S input to be 1 and my R input to be 0. And if you observe at the output, you could see that my Q is 0 and my Q bar is 1. So let's look at that on this table. When S is 0, when S is 1 and R is 0, you could see that the Q state, or the next state of Q, is 0, and obviously Q bar will be 1. So if my S is toggled to 0 and my R is 0, you could see we have both states are high. That is, Q is 1 and Q bar is 1. And in this state, we call it indeterminate, because you should not have both Q and Q bar state to be the same state. At this state, it's called indeterminate. So to implement our whole state, which is just memory state, let me implement when my S is 0 and my R is 1. So you could see here that my Q toggles to 1 and my Q bar is 0, when my S is 0 and my R is 1. So S0, R1, Q is 1, as you can see here. So if I toggle my S state to 1 and leave my R state as 1, you could see that the state of Q and Q bar remains the same. And that's what we call the old state or the memory state, meaning that the previous states of Q and Q bar remains the same in the next state when you change the inputs combinations of S and R respectively. So yeah, you could say that Q still remains 1 and Q bar remains 0. And so that's how we test our SR latch to be sure that we have it connected properly. So next, so for step 3, what we're going to be implementing is to use our SR latch. We're using this push button that we implemented in step 1 to drive the inputs into our SR latch. The next step is step 3, and I'll be showing us exactly what we're required to do in step 3. So for step 3, we are literally using our push button as the inputs to our SR latch. So instead of what we did in step 2, where we used our DIO 0 and DIO 1, we'll be using the push button to supply our S and R states into our SR latch. So to set up this, for this stage, the setup has been done on the left-hand side of the board. So I'm using the second push button here to implement my inputs for my S and R. And then this is my 7400 NAND package. So the NAND connection, the SR latch implementation on this NAND gate is exactly as it is done in step 2. But to implement the input into my S and R, I have my C, which is the center. This is a 7400. You could see the orange wires are supplying input from the push button to the 2 NAND gates, both left and right. So my S is the input connected to the NAND gate to the left of my 7400, and my R is connected to the NAND gate on the right hand side of the 7400. And similarly, we have our Q and our Q bar feeding the inputs of both left and right respectively. But how did I implement my S and my R? To implement the inputs into my S and my R, I used a pull-up resistor. So the pull-up resistor is connected such that if there's a 5-volt supply to the resistor serving as a terminal between a junction between my push button and my S and R input. So my normally closed is connected to my S input through my normally closed goes through this wire trace, this orange wire trace, to one of the resistors that's connected to 5 volts, and the other end goes to my S input. Then my normally open, which is the black wire here, goes to my R input through this resistor package. So how does this work? The center, like I showed in step 1, so instead of connecting to 5 volts, it's now connected to ground. So what is happening here is this, like I said, explained for step 1, this center is normally latched by default to my normally closed, which is the yellow wire here. So meaning that this is going to be pulling this normally closed to ground. So meaning that my normally closed will be in the low state by default. So when S is 0, definitely my normally open will be 1, would be 1. Why? Because I have a pull-up resistor. So the pull-up resistor pulls this particular input to the high state. And so when it's high, meaning that the reset, which is the input into the second NAND gates, will be 1. And when your S is 0 and your R is 1, like we demonstrated in step 2, meaning that your Q will be 1 and your Q bar will be 0. That should be the output states of Q and Q bar respectively. So that can be seen in figure 5 in your lab manual. To have a pictorial view of that, go to figure 5 in your lab manual as being displayed now. So what you have here is, you could see that we have the two 10K ohm resistors are connected to 5-volt sources respectively, and the junction of each of them is connected to the push button. So at this state, we have our center here indicated by always latching onto the normally close. So we have the normally close connected to my S input of the first NAND gate, and then my normally open terminal is connected to my second input, the input of the second NAND gate via these two resistors. So these two resistors are serving as pull-up resistors because at this state, when the C is connected to normally close, you have a low state supplied to your set input, your S input. Why? Because your C here is connected to ground. So connecting to ground means it pulls it down to 0. And so when S is 0, like we implemented initially, you have your Q to be 1. And then your R here is pulled to 1 by this resistor, 5 volts pull-up resistor. So this is 1, and then your Q bar will be 0. And so you're able to implement what you have in step 2 here using the push button. I'm going to show how this is done using the oscilloscope. Okay, so what we are trying to do here is to implement the debounce states and to implement the difference between the raw signal that comes from the push button and the debounce state that comes from the output of your SR latch. So to do this, we'll be using the soft panel oscilloscope here. The oscilloscope here is one of the soft panel of the Elvis board that you can use to monitor the terminals, the input and output of any of your circuits. So what step 3 is actually requiring us to do is to monitor the difference between the raw signal that is being generated from the push button and the debounce signal that we see at the Q output of your SR latch. And this is just basically trying to show us the indeterminate state when you hold down your push button in order to create a change in state. There's a principle called electrical arcing that goes on when the button is being pressed down and it's trying to make a contact between switching from the normally closed to the normally open. In order to be able to hold the current state and have a fine change in state, that is why we are using the SR latch, to be able to hold the current state. So I'll be showing that on the oscilloscope. Now the oscilloscope has to be set up in such a way that you're able to capture the different bounces of the raw signal from your push button. To do that, in the lab manual, you would see the instructions under step 3 on how to make a connection to connect to the oscilloscope using the BNC 1 and 2. So to make a connection to BNC 1 and 2, you could see right here, I have my BNC 1 connected to my R input to monitor my R input, which is the right side of my 7400. And I have my BNC 2, which is the second purple wire here, connected to my Q, which is the output of the first NAND gate. The first NAND gate where I have my S input connected to as the input. Then ensure that you connect the negative terminal of BNC 1 and 2 to ground, as indicated by this blue wire connected to the power rails that goes to ground. So there are some settings we need to do on your oscilloscope where you have to select the channel source to be channel 0 and channel 1, because these two settings are able to capture the sudden change or the state change in your push button when you press and you release the push button. Then you need to set the probe for both channels, the coupling type, which is DC. You need to set your scale to 2 volts per division. And then you need to set your time base to 50 microsecond. Then your triggering type to hedge. So you can actually capture the transition as it moves from 0 to 1. Then slope to rising. So we can have a positive hedge capture. And then we're setting the level to 1. And then our source to channel source 0, channel 0 source. And then the horizontal position to 20%. And we want a continuous mode capture. I'll be showing that right now here on the oscilloscope. So looking at the oscilloscope channel, you could see that we have the different setting. So one thing you need to do is to enable both channels. So you can have the 2 channels here. So you could see my channel 0, which is the first channel where I have my higher input connected to, is indicated by this green color. And my Q channel is connected to channel 1, which is indicated by this blue color. So you could see that the settings are done. The probe, the coupling for both sides. And then we have the scale set to 2 volts for both. And then the positioning set to 0 and -4 for your oscilloscope, on your oscilloscope terminal channel window. And then you have a time per division set to 50 microseconds for the resolution. And then your source selected, level to 1. And then you have your horizontal position to 20%. So you could use this bar to move it, or you could use these 2 arrows here to change, or you could just select and type in the right percentage score. And your acquisition mode is here, which is select to continuous. Select continuous. So if you run this, I'll be showing us exactly how this is done. So when I press my push button, you could see, as indicated by the green signal here, you could see several states of changes from 1 to 0. So all these are unstable states because of the bouncing nature of the arcing or the mechanical bounce between making contacts, between that time of making contacts with, from normally closed to normally open. You could see that you could see several bounce states, and it's as a function of the partial contact that you have before you have a firm grip to the normally open terminal. But if you see on the Q here, you could see we have a very clean change in state from 1 to 0 here. And that's exactly what you are required for or to show in this particular step. And like I said earlier, that the reason for this is because we have our C connected to ground, as shown in figure 5. You could see that our C is connected to ground. So C being connected to ground, you have C connected to ground, which is connected to your sets inputs. Will leave our Q to be 1. And so when we push the button and it moves from normally close to normally open, it toggles from S to R. Then our Q moves from 1 to 0. And that's what we have when we press the button, which I will demonstrate once again. So when I press this button, you could see Q moves from 1 to 0 because now it's in the open state, meaning that the C, which is the center, is now latched on to normally open. But you could see that because I'm reading the R inputs, when R is trying to move from 1 to 0 state, you could see several changes we have here, unstable changes before it moves to 0. So this is the 0 here state, and there's the 1. And then we have several changes in state because of arcing or mechanical contacts that we have until it actually stabilizes here. So that's the difference between the raw signal and the debounced signal. So we're moving now to step 4. So in step 4, what is required of us in step 4 is to literally use our connections in step 3, which is the push button connected to serving as our SR input into our latch to serve as our clock source into our counter. So for your 74161 4-bit binary counter, which is just right here, you can see it's wired up. You can look at previous lab manual, which is, you can look at lab 3. The lab 3 manual actually has the setup connection steps. So pin 2 on the 74161 package is your clock input, as indicated by this white wire that we have here. So what I'll be demonstrating here is to show us the difference between using the bounced signal and using a raw signal to serve as our clock source, or to serve as our clock source in order to increment the clock sequence or the count sequence of our counter. So just to refresh our memory on how a counter works. So a counter counts based on the bit size. For this particular experiment, we're using 4 bits. We're using all the 4 bits, which is the QA to QD. So it means that we count from 0 to 15 and it's going to roll over back to 0. To do that, we're using the clock source to actually increment the sequence from 0 to 15 in that order. And how to do that, we're using this push button to serve as our toggling source for our clock. So unlike using the dials that we used previously in the other experiment, we are using the push button this time. And so how do you change, or how do you count here? To change a sequence or to count, you implement a clock sequence or a count sequence. When you press and you hold, leads to a change or increase in count. So to show exactly how this counter works, I have my debounced signal. That is the output of my SR latch, which is the Q, which is just right here, which is pin 3 here, which shows the output of this first NAND gate here, where I have my hex connected to. It's been tapped in by this white wire, and I feed my counter, which is pin 2, the clock source of the counter. So when I keep pressing this, observe that my QD to QA goes through this purple wire and this gray wire to connect to LED 0 to LED 4, to LED 3, sorry. So my LED 0 is my LSB and my LED 3 is my MSB. That's the most significant bit. So as I begin to toggle this, I'll start over from 0. So this is 0, meaning that we have a clean count from 0. So as I begin to toggle and release, you can see my counter sequence increments. So that's 3, this 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and rolls over back to 0. So that's implementing the debounce signal. That is the signal at the output of your SR latch. So in contrast to that, we can also observe the raw signal that is taken from either the S or the R. That is the signal that comes into that feeds the SR latch. So to do that, I'll be showing us how this is done. So I'm taking this white wire, which I'm disconnecting from my Q, and I want to connect it to where my R is. So my R is just right here. Right. Yeah. Okay. So I have that set up. So observe the state as so pin number 15 is where I connected my R latch into. So I'm also tapping from that using this white wire to serve as my clock source, because these are the raw signal that's being fed
from my push button. So as I press and release, you could see that the count sequence skips several steps and jumps. So if you look at this, we have a 0101, that's 5. Press and hold again, we have 5. Then we have a 0111, that's 7. We have a 0010, that's 2. So what is happening here is that you have several steps skipped. It has already counted, so it skipped 5 to 4 to 15, rolls over back to 0, skips 0 and 1, and then we're now seeing 2 being displayed. We could see 0, skips, it keeps 1 and 2, it's showing 3, skips 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and what's displaying is 15. Then skips 0 and 1 and 2, and displaying 3. So we have, so this 0, 1, 1, 0, that's 6. So it means it skipped 4 and 5 and displaying 6. And so this is just basically the kind of patterns you see for raw signal, because at this state we have several switches, several counts. So that means it's already counted several sequence, it's already incremented the count. And so when it reaches a state in which is stable, you could say that actually counted, it already incremented the count sequence. And so it's more like it's skipping some of the counts. And so you don't have like a stable count increment like you should have if you have a debounced signal. And that's basically all for this particular lab. I hope this would help you and guide you through understanding the lab better. If you have any question, you can always reach out to your GTA. Thank you for your time. Have a good day.